Hello everyone, this is Payman and I'm preparing this video on tutorial 4 of ENGR 350 for those who cannot attend the Tuesday session. So we are covering a couple of questions in three-phase circuits in this tutorial. The first question you can see on the second slide actually, and it's a three-phase circuit. As you can see, we have a three-phase source here. And let me use a laser pointer. Okay, so we have a three-phase source in here and then three impedance connecting the source to the Y connected load here. So it wants us to find the currents of line IA, IB, and also IC. So generally we know that the phase voltage VAN is lagging the line voltage by 30 degrees and the amplitude is divided by square root of 3. So if we want to find the phase voltage, we say the line voltage, line to line voltage, multiplied by 1 over square root 3 and lagging by 30 degrees. So here we have the same equation and the line voltage is 440. We divide it by square root 3 and the angle is lagging the line to line voltage by 30 degrees. So the line to line angle is 10 degrees for VAB and we subtract it by 30 so that we have VAN. So the line current is the phase voltage over the impedance of one phase. So we have 440 over square root 3, which we got in this equation here. And we can divide it by ZY to get the current. So what is ZY? So ZY is the series connection of the impedance of the line and the Y connected load. So we have the impedance of the line here 3 plus 2J and the impedance of the load 10 minus 8J. So it results in 14.32 with the angle of minus 24.78 degrees and it's in ohms. So we can find the line current, which is 440 with the angle of minus 20 degrees over square root 3. So this part is the phase voltage over ZY and it will give us the current, which is 17.74 with the angle of 4.78 degrees and it's in amperes. So now we want to find other phases current, and in a positive sequence we know that the phase B current is the phase A current, which is lagging by 120 degrees. So we multiply it by 1 with the angle of minus 120 degree and it will give us the number 17.74. So the amplitude of the current is the same in phase A and phase B, but the angle is minus 115.22 degrees. So there's the same story for IC, and this time we multiply IA by 1 with the angle of plus 120. So the current of C is leading the current of phase A by 120 degrees, or we can say that it's lagging by 240 degrees. So we have the current for phase C as 17.74 with the angle of 124.78 degrees. So this is the first problem we had. It's pretty easy. You just need to know the relation between the three phases and we can solve this problem. Then we go to problem 2, which asks us to find the magnitude of line current in this circuit here. So we have line impedance, three similar line impedance in three phase, a delta connected load with Z delta and a Y connected load with ZY. So we see that it's a balanced line. So we have three equal impedance in the line, a balanced delta load, we have three equal impedances, and a balanced Y load. Amount of the impedances are given and it is per phase, so otherwise stated the value of impedance is per phase and has nothing to do with the three phase. So we want to find the magnitude of the currents coming from this node IA, and which is the same in magnitude for IB and IC. So the first thing we need to do, we want to solve the question, the problem in per phase basis. So we need to get rid of delta connections. If we have a delta connected source or a delta connected load, we want to get rid of it. So for finding the equal amounts of the delta connected load in Y connection, we calculate this ZY E, which is the Z delta over 3. So it means that if we use a three-phase delta connected load with Z delta, it's the same as if we use a three-phase Y connected load with ZYE. So the amount of ZYE is 8 minus 10J. And if we want to calculate the equal impedance of the two parallel loads, so we had one originally Y connected load and we transformed the delta connected load into ZYE, so we want to see what's the parallel equivalent impedance. So ZP equals the parallel of these two, and it will give us this number 8.076 with the angle of minus 13.68 degrees, which is equal to 7.812 minus 2.047 J ohm. So the total impedance the source sees in this connection is the series of line impedance with the ZP we just calculated, which will give us 8.847 with the angle of minus 6.78 ohms. And then the amplitude of the line current, so we here only care about the amplitude and not the angles. So it's the phase, the voltage of phase, the amplitude of it, and also the amplitude of ZT. So the voltage of phase is line to line voltage over square root 3, and the amplitude of ZT is 8.847. So it's the same number we see here. And it's equal to 13.66 ampere RMS. So why we say ampere RMS here is that, like in three-phase question and three-phase problems, whenever they don't mention that something is the amplitude of the voltage or RMS value of the voltage, we just consider it as RMS and not the amplitude. So otherwise, they will say that the number we've given to you is the amplitude. So here they didn't say anything, so we presume that this is the RMS. So their calculation was based on RMS, and the final answer will be ampere RMS. So then we go to problem 3. In this problem we have a three-phase delta connected source and a three-phase delta connected load. So amount of ZL is given 10 plus 8J, and we have a three-phase source with 230 volts, which is RMS because they didn't say anything. And so we have the voltage of A to B with 0 degree, the voltage of B to C with minus 120, and voltage of C to A with plus 120. So he wants us to find the current of IAC, which is the current following in this branch IA to IC, and IBB, which is the current following in this little branch here from small b to capital B. So in order to find that, we want to see what's the voltage across the AC branch. So we go back to previous slide. So from A to C, the capital B is connected to the small b, and the capital C is connected to the small c. So the voltage across here is the same voltage that will be applied across AC. So we can say that IAC is minus 230 with the angle of 120, and over the impedance of the branch, which is 10 plus 8J. So it will give us the number 17.98 with the angle of minus 98.66 ampere RMS. And to find IBB, again we go back to the question figure. We see IBB, we can say it as IAB minus IBC. So it's writing a simple KCL here. You can see that we have two incoming currents and one outgoing current, and with that you can find IBB in terms of IAB and IBC. So with the same story we can find IBC and IAB, so the voltage across the branch over the impedance of the branches. And it will give us IBB equal to 17.98 with the angle of minus 158.66 minus 17.98 with the angle of minus 38.66. And the result will be 31.1 with the angle of 171.34 degree ampere RMS. So we see something here that's IBC and IAB have the same amplitude as IAC, but a different angle. So which is something we expected, because it's a three-phase balanced circuit, and only the phase will be different in different phases, and the amplitude is the same for all the phase currents. So this was all about tutorial 4. If you have any questions or you have difficulty understanding a part, please email me and we can set a time to talk about it, or you are very welcome to join the Tuesday session on 11 o'clock. So Tuesday, library 306. We have the tutorial session for this week in that location. Thank you very much for